Welcome to this next video for the reverse engineering course of Learn Security. This video is associated with chapter number 12 of the reverse engineering course. Once again, through this video, we are going to see in practice the anti-reversing tricks we discussed about during the written part of this chapter. So let's try and run the application. We will notice that it will not even start. So let's load it with Ollie Debugger and run it. We're going to see that the execution stopped here, and as we can see, there was an interrupt-free instruction executed in this address here. So as we said, the interrupt-free instruction is basically a software breakpoint. It's actually a trap the debugger is going to raise a specific exception, which will make the debugger think that someone has entered the breakpoint there, so it will make the execution stop. Of course, we didn't put any breakpoints, so we can understand that this interrupt-free here is quite dodgy, so we'll have to see what's its real purpose. Let's just step into this call for now and see what is going to happen. We're going to see that the terminate process API is going to be called, and this is going to kill the process. So we know that this is an anti-reversing trick, and what we need to do is to instruct the debugger to always pass the interrupt-free instruction to the exception handler of the application and not treat it itself. Unless, of course, it's a breakpoint that we have set. So we can go to Options, Debugging Options, Exceptions, and instruct the debugger to always pass the interrupt-free breaks, these instructions here, to the program, so that it will handle the exception. So let's now run the application and see what is going to happen. Now the application died. We can see there was a call to the terminate process from this address here, which is the same function, and we can also see here that there is another return address from another function. So let's follow in this assembler and see what was the previous function called. So the previous function called was here. So we can see what's inside here. It's the terminate process. You can see. So if we go there, we can see that if this jump is executed, it's going to bypass the call to the function that contains the call to the terminate process API, and we can also see a function just before. So I'm going to put a breakpoint here and run, and now as you can see we stopped here, and we're going to examine the function that is going to be called now. So let's just step in the call, and we can see here that there is a call to the find window API, which tries to obtain a handle to a window with this class name here, if the window of course exists, and it's the topmost window of an application. So this, as you can see, it's quite obvious that it's going to be used to detect VirtualBox, and you can see the class name, which is VBox tray tool WND class. If you go here in the tray area, you can see the tray of which that the VirtualBox places here, the tray icon, and this is its class name. So we can detect VirtualBox just by using the tray icon. So since we are using VirtualBox in order to run these applications, This API is going to return a valid handle, otherwise it should return 0. So it will return 1 to EX to AL. So it's going to call the function that terminates the process. So let's restart the application again. Run. We stop here. What we can do is that instead of patching the API, for example, we can also patch the code here so that it will always jump. It's always better to patch the API code so you don't have to care how many times the same check is going to be performed. But let's also use this way. So now this is going to return 0. Now the application is going to run. So by now we have identified two tricks. We have identified a debugger detection mechanism through exceptions by using the interrupt 3 instruction, and we have also identified the VirtualBox detection mechanism. So let's restart the application and see now if we can identify any other tricks that were not triggered till this point. What we know is that the application is going to call the terminate process API in order to kill the process if an anti-reversing trick is triggered. So let's place a breakpoint here. And we can also re-enable this patch in order to bypass the VirtualBox check. So let's run. What we can see now is that the application crashed in a very strange way. There is an access violation, executing an invalid, trying to execute an instruction in an invalid address. We can see that the ape points to an invalid address. Let's now observe the stack. We can see here that there was a call at this point, returning back to this address. So let's follow in this assembler. And we can see there is a call here. Let's just press enter to see what's inside. We can't find anything interesting. So let's scroll down further and let's examine this entry here in the stack. Let's press enter just to see what's inside here. We don't see anything interesting. Let's do the same for this entry here. So by using the stack now, we didn't manage to find anything interesting. But still, we have the first entry here that we didn't examine. So let's follow in this assembler. And we can see here some very interesting code. We see that here is going to execute the RTTSC instruction, which reads the day timestamp counter register, which is 64 bits register, so it's going to split the value into EX and INDX. In INDX is going to be placed the 32-bit high D word, and in EX the low one. So it seems that something went wrong at this point. This is very dodgy, because it's going to call EX after executing the RTTS instruction, which at this point DX will most probably will never contain a valid address after executing this instruction here. So let's put also a breakpoint here and see what happened and understand when this conditional jump is going to be executed to skip this instruction here and the call EX. So let's restart the application. let's enable the patch. And let's go to the terminate process. We already have a breakpoint here. Let's run. So now we stopped here. We still have control on the application, it didn't crash. So let's step in. Let's see what happens. We see that it's going to load the kernel 32 DLL. We can see the image base returned in EX. Then we can see that it's going to retrieve the address of the terminate process API, which is the API we previously placed a breakpoint. So now the address of the terminate process API is in EX. And what it's going to do is actually checking if the first byte in the code in terminate process is equal to CC hex, which as we know is the opcode for the interrupt 3 software breakpoint. And remember that we have set a breakpoint here. As you can see, Oli says that this is indeed 8B, the first byte, as it should be, but in reality it's not. So when it's going to compare, you see that jump if not 0 will not be executed, which means that the comparison actually matched the CC byte. So it's going to return 1, and then we know what's going to happen. So let's now go back here and remove the breakpoint from here. Let's do the comparison again, step over once. You see now that indeed the first byte is not CC anymore, so it's going to jump. And what it's going to do is going to compare also the next byte. So it checks if there is a breakpoint at the next byte, and then the next one for the first 5 bytes. So if it doesn't find any software breakpoint among the first 5 bytes, it's going to return 0 and exit the function. So 0 is going to be decremented, it's going to become -1. So jump if not 0 is going to be executed, and we bypass also this trick. And then there is another one called here that if we can see again that if the jump is not executed, it's going to call the function that's going to terminate the process. So most probably there is another trick here which we are going to examine right now. So let's step in. We can see that the application is retrieving the ID of the current thread, and then it obtains a handle. You see that the handle number is returned in EX and is going to save it into a local variable, and then it's going to read the context of the thread. You can see that the getThreadContext API receives 2 parameters. One is the handle to the thread, and the other one is a pointer to a context structure. So it fills the context structure with some values. Depending on the flags. So as you can see, it's going to check if at this address here, EBP-2D0, which is at the address 12FP74 here, if this value is 0, and then the next one, and the next D word, and then the next D word. Now, here are, in these values, in this position here, there must be the values of the debug registers. which, since we haven't set a hardware breakpoint, these are 0. So this is going to return 0, and then, as we know, the next trick is going to be executed, which now we bypass, which can just run, and then we arrive here, and then the application runs. So let's make a change in order to see also the trick regarding hardware breakpoints to be triggered. Let's go on the terminate process and set the hardware breakpoint. Now let's enable also the patch regarding the virtual box detection. Let's run. So you can see here that the hardware breakpoint in the DR0 hardware breakpoint here, the debug register. So let's step in. It gets, again, as we saw, the thread ID, then it receives a handle to that thread, and then it's going to read the thread context. So let's follow in dump again. Step over once, and we can see now that here the DR0 contains the address of the hardware breakpoint. So when it's now is going to check, this is not 0 anymore. So this is going to jump, it's going to return 1, and it's going to call this function that terminates the process. So once more, we successfully managed to analyze all the tricks and also bypass them. We saw also how they work and how it's possible to trace back again from the stack in a more complex scenario and find a trick that we didn't know it existed. I hope you had fun again with the last part regarding anti-reversing tricks, and see you in the next video.